Bonjour, est-ce qu'on m'entend? On m'entend, oui. So this talk is in English because English is my mother tongue, and I thought, what better way to wake people up than to speak English? So yeah, it's the only one in the entire conf, so bear with me. You'll be able to ask questions en français à la fin de ce talk, but until then, it'll be in English. And so I really wanted to start off with asking you all and asking us all to think about why we code. Indeed, why do we code? Why do we code? I really want you to think about this question for a second. And when I think about this topic, I see several reasons. The first one being that it's just fun. I have so much fun when I code, and I can lose track of time. And I do, every day, luckily. Maybe you love how to code because it allows you to create beautiful either architectures or pieces of software, and you see beauty in that. Maybe it is the depth and difficulty of the technical challenges that you're facing that make you happy to code every day and to really show to yourself that you're capable of tackling these challenges head on. Maybe it's because of how coding makes you want to 1 second pull your hair out, which happens to me a lot, and the next makes you feel like you're Lionel Messi having just scored a goal at the World Cup final. Obviously, this is not Messi, but you get the feeling. Maybe you're like me and you're a Swift junkie, so you love the Swift programming language. Or maybe you love that sweet, sweet moolah that you get at the end of the month for coding. My point is that all of the best software products, all the best products, they share certain common traits. They are scalable, meaning that they can handle 1 million, or even 250 or 1 billion users in the case of Facebook and Meta, without losing the quality of the experience, of the user experience, and without degradation in service, and they can handle that extra workload. They are also maintainable, meaning that it is relatively simple, as easy as it can be, to change a feature, modify it, remove it, add a new one, and augment the experience over time without breaking the entire system. So yeah, maybe we should call maintenance once in a while on our software. Lastly, the best products are secure, meaning that as a non-connected user, you won't be able to get points or do something that not connected users should be able to do. You'll also not be able to escalate privileges, in theory at least, but we all know that there are huge vulnerabilities in our software. The best products, digital products, are also stable, meaning they don't do what this EasyJet plane is doing right now, and they don't crash as soon as you use them. And there are lots of opinions on how to reach the result of having scalable, secure, stable software. And I'm here in front of you today to actually give you an opinion on how to reach that state. But before I do that, I really want to preface that with everybody in software engineering has opinions. That does not make them true. So take all of what I'm about to say with a huge grain of salt. And so there's really been like a whole bunch of opinions on how to reach that state. And we've come up with a whole bunch of different ideas. Some of them are architectural patterns, like hexagonal architecture or clean architecture. But we've also come up with, and this is going to be the topic of today, with design principles, like clean code, like KISS. Does anyone know what KISS stands for? Yes? Yeah, you've just earned yourself a cookie. Congratulations. If you want to come and get it. So yeah, you should keep it simple, stupid. Congratulations. They're delicious. You'll love them. And so what I was just saying is that there's a KISS principle. There's the dry principle. That doesn't count because I prepared it with you. Yagni Anyone know what Yagni is? I think you said it, right? Yeah, okay. Congratulations. More cookies for you. Enjoy. Okay, so that was my attempt at waking people up after lunch. And then the last, but certainly not least, what we're going to be actually talking about today, that was difficult, is the solid principles. And again, all of these share the same overarching goal, which is to craft better software that is testable, maintainable, scalable, secure, and stable. Now, I'm not here to tell you that if you follow those solid principles, you're going to have scalable and secure software out of the box. We all know that security depends on procedures and alerting and all that sort of stuff, and I'm not a security expert, so I'm not here to talk about that. Likewise, scalability, as we all back-end people in this room knows, depends a lot on your architecture, your infrastructure, and how you've built it up. My point is, by following these simple design principles, you can drastically improve all of these and make it easier to test, maintain, scale, secure, and stabilize your software. Have I lost you yet? Wakey, wakey. So yes, this talk is called Rock Solid Code and using the solid principles to write code that stands the test of time. So now it's question time. And if you can, only if you can, we're an inclusive conference, please stand up if before coming into this room, you'd heard of the solid principles. I'm Slim Shady, yes, I'm Slim Shady, Alden is Slim Shady. Okay. Please stand up. Please don't sit down. Don't. Everyone who's heard of the solid principles before, please stand up. Awesome. So I see that we've got a good contingent. That's a good thing. Now, please, if you can, sit back down if you don't know what each letter stands for. Stay standing up if you know what each one of the solid letters stands for. Ooh, this feels like Hunger Games, or Koh-Lanta, à la fin il n'en restera qu'un. And now, the last question, who actually uses the solid principles on a daily basis? Okay, so to the heroes who are still standing, a round of applause. So our goal today is going to try to see how we can all be like Johan and understand what the solid principles are and use them in our day-to-day as developers. So let's jump right in. I'm going to start off plain and simple. What are the solid principles? And let's dive into the first one, the first letter, the S. So the S stands for Single Responsibility Principle. And this is a live video of me running away from my responsibilities, or more importantly, from my class running away from all its many responsibilities because it has too many responsibilities. This principle calls for your classes to have only one reason to change. And so it follows that you should have only one reason for being per class, and you should be able to state that in a simple manner. So you've seen me give out cookies and bribe you with sugar in a completely unacceptable way. So now what we're going to do is we're going to be building pseudo software. This is not real. I haven't compiled it. And it's going to be a cookie delivery service. It's like going to be Deliveroo for cookies. And so this is me before I learned about the solid principles. I would have coded, imagine a backend with an endpoint, and I would have just called an order management class in my router and just saved the order to the database, calculated the total, and send the order to the restaurant all in one single class. So this is bad, and this is really bad. I know that in my code base, there's definitely that. I'm sure in a lot of code bases that you work on, you've either seen it or you've dealt with it. But I really want to drill in on why this is wrong. So can someone, for one cookie, I will give one cookie to the person that tells me why this is bad. I've explained the principle. I'm showing you the code. Okay, so we're all sleeping. Okay, so you know that the principle is that a class should have one reason and one reason only for being, one responsibility, the single responsibility principle. So could someone describe what there's actually 3 different responsibilities here, and it is to save the order to the database, to calculate the total of the order, and to send it to the restaurant. And because I found the answer, I get a cookie. Okay, so no one found the answer. Hello. And so basically, the solution to this problem is breaking out our 3 functions into 3 separate classes. And so you're going to see this image a lot. It's an image of a banana split. And basically, we're going to split it. And so the way we do that is we have a first class called the order repository that is going to save the orders to the database. Sorry. These are delicious. We're going to have a second class called order manager that's going to calculate the total of our order of cookies. And we're going to have a third class that's going to interface with the restaurant. By the way, I didn't mention it, this is Swift code because I don't write Java or Kotlin, I'm sorry. And so the way you declare this, and then you'd have your router, and every time you handle the order, you would call the appropriate object for that. This is really pseudocode. This is not meant to be any sort of real code. And so the next principle is the open-close principle, and this one for me is the hardest to grasp. So I suggest that you pay double the attention to this one. And there's more cookies to win, more sugar. And so basically this principle states that classes should be open for extension, but they should be closed for modification. So what does this look like in real life? Let's imagine I have an enum. So for those of you who do Java or Kotlin, it's an enum class, I believe. And so basically, we're going to give a bunch of cases for our different cookies. So we've got a white chocolate chip cookie, a dark chocolate chip cookie, a milk chocolate cookie, chocolate chip cookie, and a caramel cookie. And then when we want to compute the price, we basically pass in the cookie, and we're going to switch over to that cookie, and we're going to implement some way of finding out the pricing of that cookie. So this is bad. It's not really bad, and I think you'll see that in a lot of code bases, and it's pretty much okay. But it breaks the open-close principle, but it's still pretty bad. And so can someone tell me why? No, still no one's like, let's go. Okay, so we have a gentleman in the front that said that I was hard-coding the data, and so when I would change my pricing policy, I would have to go and change the hard-coded values. That is 100% true, but it's not the reason why we're violating the open-close principle. We're violating the open-close principle because, again, what happens when I want to add a new type of cookie, which is highly likely to happen? I would have to go to my enum and add a case, which would then break the open-close principle because my code would have to be modified. And so, yeah, I've been spoiling myself. So how would we go about fixing this? A lot of people think that Swift is a object-oriented language, when in fact it isn't. Swift is a protocol-oriented language, and so basically what we're going to do is we're going to start with a simple protocol. And this protocol is going to be called priceable. When you name a protocol, or what we call a protocol, you call an interface in the Java world, Apple recommends that you either give it a noun, able, ing. And so here I went priceable. And what I'm basically saying is that conforming objects to this interface will have to implement a function called compute price that will return an integer. And then what I'm going to do next is a little bit of renaming. And so instead of calling my enum cookie, I'm going to call it cookie type. And so I'm going to have all the different kinds of cookies I have. And so now I'm going to add some more protocols, because we want protocols everywhere. And so we're going to call this protocol cookie cuttable, and we're going to declare a variable of type cookie type. Oh my God. It's a variable called type of type cookie type. With a name of type string, a price of type integer, and a bunch of ingredients. So far, so good? Okay. And so then for every single time I'm going to create a new cookie, I'm going to make it conform to my cookie cuttable protocol and my priceable protocol. And so for my white chocolate chip cookie, I'm going to do what the gentleman in the front suggested and implement the own logic on that class for the requisite type of cookie. And so basically, every single time I'm going to create a new cookie type, I'm going to create a class that will allow me to implement that calculate price logic. And I'll do the same thing with the dark chocolate chip cookie, and I'll be able to decide that for the dark chocolate chip cookie, I'm going to multiply the amount of ingredients by 3 and add 10, and that's the price for some reason. Don't ask me why. Next up is the Liskov substitution principle. And it's actually one of my favorites because a woman called Barbara Liskov came up with it. What this principle essentially states is that objects of a superclass should be able to be replaced by objects of its subclasses. So I like to sum this up as display cookies aren't edible. Let me explain. Imagine we have a class called cookie, and that cookie has a name, because forget about the cookie type, enum, for a second. And then we're going to have an integer that counts the amount of bytes that have been taken. So now imagine if we have create a new class called display cookie, and we make it, we declare cookie to be its superclass. And so we're going to override the function called eat, and then we're going to throw a fatal error because, as you all know, display cookies aren't suitable for consumption because they're either rotten, they're real cookies that are rotten, or they're plastic. So what I'm trying to get to with this example isn't just that display cookies are plastic or that you should not eat them, is that sometimes when we write code and we have a subclass with a parent class, we don't make them swappable. And so this really doesn't help with maintainability or that sort of thing, because you can't swap out the two classes because one of them is making assumptions and the child class is making assumptions that aren't right. In this case, the display cookie, we're making the assumption that it'll be able to be edible when it clearly isn't. And so here you've got a class, a simple clash of my logic with the way I've designed the cookie. And so, fixing it is as simple as cookie and display cookie having a sort of balanced out logic and being smarter and not assuming that subclasses will implement a eat function. And that will allow them to actually be able to be swapped out. Next up, we're soon arriving at the end of the list of the different principles. So right now, we've done the S, we've done the O, we've done the L, and now we're at the I. And so this one is called the interface segregation principle. And this one states that clients should not be forced to depend upon interfaces that they do not use. And so basically, this means that you should start with a protocol, And so again, we have our old cookie protocol that has a name, the same cookie type, the ingredients, and the compute price function. And now we're going to make a free cookie. So we're going to do what I'm doing and hand out free cookies at our store. And so we're going to have a type, we're going to have a name, we're going to have a bunch of ingredients. And then we're going to try to compute the price, but there's going to be a fatal error. So it's going to crash because free cookies don't have a price. And so this is a classic case of this protocol not being segregated enough. And so it's forcing conforming objects to implement parts of an interface that they do not need. Our free cookie does not need to have a price. And so essentially, what I'm gonna invite you to do is to first of all think about how you would fix it, because we want free cookies. Any ideas of how to fix this? We've got this protocol, and we don't need the compute price in it for our free cookie. So what would we do? Yes, I've heard it for several people. So if you've said the right answer, come get your cookie. If you want it, you can also say no to free cookies. It's weird, but crazier things have happened than people saying no to free cookies. I also heard it up there. If you want to come and get it, you're good. Okay. We found someone who says no to cookies. That's interesting. Anyway, my point is, if there was a really smart person, sorry, if someone wanted to be a little bit, and seeing where my logic isn't perfect here, you could say that instead compute price in the case of a free cookie could just return 0 because a free cookie doesn't cost anything. But for argument's sake, this is let's pretend like we want to banana split it again. So basically, we're going to declare a protocol that's called priceable. We've seen this protocol before. And basically, it's going to allow us, water. And basically, it's going to force conforming objects to implement a method called compute price. And so now, instead of having I see I've inverted 2 slides, and so now it's just not acceptable. But anyway, now when we do that, the free cookie just can conform to cookie if we remove the priceable protocol. And essentially, what we've done is we've segregated 2 interfaces, and so we have one interface for cookies in general that's called cookie, and we've got one interface that's called priceable for forcing conforming objects to implement a method to compute their price. And so basically, for all the other cookies, you make them conform to cookie and to priceable, and for the free cookie, only to what he needs. And so that avoids you having to implement the issue with the fatal error. You could also just not throw a fatal error, but that's another story for another day. And so now we've reached the last one of the solid principles, and this one is the dependency inversion principle. So what does this one state? High-level modules should not depend on low-level modules. Both should depend on abstractions. So concretely, let's look at this code. And now you're not wiggling out of this one, guys, because it's the last principle. And so I need to know, and I want to give away cookies. Where is the issue with this code? Like, imagine yourselves, you're in code review, you've just been asked by your product manager to implement a email and SMS notification system to inform people when their cookies are ready to be picked up. And you see the junior software engineer on your team called Emma come up with this code. What do you do? he said a super important thing, which is this is not really testable. And that's the biggest problem with this code. But why is it not testable? Let's go deeper. That's a super good. Oh. So the gentleman up there just said, "What if I want to send notifications with SMS?" That's a really valid point. So it's not testable. What if I want to send SMS? Okay, people, more ideas? No? No one? What if I told you that these two classes are they're too coupled? They're basically not enforcing the dependency inversion principle. So the problem is that they're too highly coupled, and that one depends on the other. And so, as the gentleman said, tomorrow we may want to do SMS, we may want to do mobile notification, we may want to do, I don't know, smoke signals or flying pigeons, whatever. My point is that you want to decorrelate and abstract, create an abstraction over the email service so that you, instead of taking as a parameter the email service, which we're not even taking as a parameter, instead of taking that email service, you could take any notification manager. So how do we fix it? Again, we start with a protocol. So we're going to start by creating a protocol called notification service. Remember, Apple tells us that we're allowed to use nouns for this sort of protocol. And so basically, conforming objects are going to implement a function called send that's going to basically send a message to our user. So as the gentleman up there suggested, we're going to want to create one email service, and our logic for sending an email is going to live in that service. And so imagine yourselves, if you know that there's a bug with the email service, you'll just have to go to that particular class, and all the logic will be there. It won't be split throughout the code base like some kind of cancerous cell. And then separately, because it's a different sort of notification, we'll have an SMS service, so we're able to send SMSs. And if you think about scalability, tomorrow, if you want to implement any sort of other notification, it'll be very simple. And then so now that we've got two types of notification, we're going to want to basically change our notification manager. And first of all, start by using dependency injection. In this case, we're passing what we call an existential. What is an existential? Is we're going to basically say, pass in a value of type service, and that value is going to be any sort of object that conforms to the notification service protocol. So tomorrow, if I want to test my logic, I can actually pass in a mock. Tomorrow, if I want to implement another type of notification, I can very easily do that. And so when we're going to use that notification manager, we're just going to call the send notification, pass in the message, and our notification manager will call whatever service has been passed in, and that will send, hopefully, the notification to our user that they should really come and get their cookies. Speaking of which, notification to the gentleman up there that gave me the idea about SMS, and there was another idea over there about testability. If you want to come in and get your cookie, you're more than welcome. And just so you know, guys, I'm all out of cookies after that, so it's just, this is it. Congratulations. Enjoy it. Thank you so much for participating. Anyway, back to our notification manager. So I just want to, we're going to move on, but I just want to first start with a quick recap. Hopefully a solid one. If you were sleeping up to now, now's the time to wake up and to just take a picture of this slide so that you can think about this later. So basically, the single responsibility principle means you have one class, one reason for being. If you see a class that fetches something in the database, sends a notification, and checks that the state of your server, there's something terribly wrong with that particular class, and you should probably consider splitting it, preferably without asking your product manager, because they'll say no. Secondly, the open-close principle, also the hardest one to understand, in my opinion. Classes should be open for extension, but closed for modification. This is the point where being a senior developer helps. Unfortunately, I'm not a senior developer, so this is what I will say. It is super important to think about how your code will scale in the future, meaning how you can handle future requirements, be they from product or just from a technical point of view. And so thinking about that, thinking about how your code will evolve in the future, even as you're writing it, is a super important skill to develop. The list of substitution principle really calls for child classes to be able to be replaced by parent classes. So hopefully child and parent classes are an easy concept to grasp. The interface segregation means that no object should conform to an interface that he or she does not need, or he or she does not need to implement, or things like that. And so if you see that you're conforming to an interface and the interface is a little bit bloated, this can be a good idea to split the interface. To hopefully you have tests that help you make sure that you haven't broken anything. If not, it's also a good moment probably to write tests. And basically to use that time to really think about your interfaces and whether your objects aren't conforming to too much of that. Finally, the dependency inversion principle calls for the lower level objects to depend on not to depend on higher level objects, and that they should both have a contract through an interface to have that abstraction between them, and for them not to depend on any concrete implementation. And so that's when you really see the power of a programming language like Swift or like Java, with that strong emphasis on protocols and interfaces. And now I really want to speed run through this last part, which is going from theory to practice. And because now I've shown you like all the principles, what they were and stuff like that, but I'm sure a lot of you are wondering, like, okay, Emma, come on, you showed us cookies, you bribed us with cookies, that's unacceptable. But how do I use this in my day-to-day? And also, why do we actually need the solid principles? Again, I spoke about maintainable code. This is what it looks like when a Ferrari, first of all, my friend Jordan said that if I should warn you guys that this image is pretty fast, and so if you want to look away if you have issues with fast images. But basically, this is what it looks like for a Formula One team to change and replace components on their product. And my dream is that on my app I could do that way. Breaking news alert, I don't know that any company does that, but that's what you should go for. Basically, the solid principles make it easier to adapt to the changing requirements because it'll make you feel more confident that you're not because of the solid principles force you to have all your logic inside of one, related to one. When you think about the single responsibility principle, for example, it forces you to have classes that have only one reason and one reason for being, so they're easier to reason about. And also you know that all the logic in your app related to a particular business logic or some sort of other logic, that it only lives in one place. And so if you've tested that properly, you're probably not going to be met with spillover effect if you change it or if you refactor it. And again, following the solid principles mean that adding new cookies or new features is as easy as creating a new class for them. As you can see in my examples, when the pricing logic changes, I only touch one function, and I don't change one huge function that computes all of the different prices for cookies. I just change the one cookie, and so that also reduces the spillover effect. Like I just said, when the pricing logic changes, I only change one function. The solid principles really force you to think about isolation boundaries. So the fact that you've got only your logic lives in one place means that it's less likely to spill over. And then again, when you're talking about maintainability, if you follow the list cup substitution principle, you should be able to swap out implementations like one base class for one superclass super easily. Finally, we want our code to be testable, right, everyone? We're doing tests, right? Even though tester c'est douter. So if you think about, for example, testing a class, the easiest classes to test are the ones that do only one thing, they do it well, and they're the only ones doing that. And so it's a lot easier to reason about the logic, and you're not sort of thinking about 150 logics and 150 different paths. It's also much easier to create fake and stubs when you rely on abstractions. So if you have, the dependency inversion principle, and you're relying on abstractions, you can just create a mock or a stub class that conforms to that protocol and mock the behavior, which makes it a lot easier to test. Finally, following the solid principles really helps with managing technical debt. And as Alison Hightower says, there is a debt to be repaid. Every single line of code we add, the clock starts ticking. But basically what I will say is the solid principles aren't a silver bullet, but it encourages you to make good design decisions from the start and to really think about and reason and think about your code in a way that makes technical debt more manageable. And for example, if you think of the list cup substitution principle, that means that potentially tomorrow, if you swap, oh my God, I almost said the name of a partner of this conference. But if you want to swap databases, out of my brain, a key value database for a PostgreSQL or something else, it will be a lot easier if you followed the solid principles. It also helps your code not to become spaghetti. As my friends know, I love Italian food. We're going out tonight to celebrate eating Italian. But I don't like it in my code base because it makes it super hard to reason about. And so the way that you avoid that is by having classes, again, that are well-defined, a single responsibility, that don't rely on concrete implementations, and that allows you to have code that is less tangled, and to manage that growth in scale and complexity as you go. We've talked about scalability before. Again, like as I've said, I'm sure there's a lot of SREs, DevOps people, and really smart backend guys, so I'm not going to go into scalability too much. What I will say is this. The solid principles won't help you if you don't have your managed instances on AWS properly configured or whatnot. I'm no expert. But it will, however, help you manage the scale of new features, new requirements, new changes in the way that you're going to build your software. And what really helps you is that scale is as simple as adding new implementations of existing interfaces, or in certain cases, if you don't have an interface for that, to create a new one, obviously. But it mostly helps you handle that growth in scale. And it also helps part of the system to evolve separately because they're not tied together, and you know that there's no spillover effect, so you can change out one part for the other, and because they rely on abstractions, you won't break everything. It also makes your code more future-proof because of the way you've separated it, you can very easily swap out one UI framework for another. And these are really powerful ideas, too, that you'll find in clean code, hexagonal architecture, and onion architecture, just to name a few. And because it forces you to make really simple, small, clear-cut classes, it'll also help you make them more reusable, so you can use the same abstractions several times in the code base. So now a lot of you will be wondering, how can I use them in my daily work? We don't have it on our pull requests, but I try to go through a mental checklist, especially now that I've done this talk, and to think about when I see a class, what is this class's responsibility? Is this class closed for modification, open for extension? Could I substitute this base class for its parent if it's a base class? If it's not, there's no need to think about it. And does this class really need and implement all parts of the interface, or could this interface be split? And again, if this class is a lower-level module, does it rely on abstractions to link up with the higher-level modules, or does it rely on a concrete implementation? Usually on my team, we're pretty good at doing dependency injection with existentials, and that's really important. So a couple of core ideas and takeaways in 1 minute, and 1 minute only. Use common sense. My favorite answer when someone asks me a question about development is, it depends, because it really depends. And each and every one of us has very different contexts, very different business logics, and very different things to think about. So these principles are really good guiding lights and really powerful ideas, especially when you understand them properly and you actually investigate them. That doesn't mean that you should follow them blindly. Generally speaking, the one idea you should think about is that solid principles really encourage you to create a code base with loose coupling but high cohesion. So your different classes are not going to be bound together, but they're still going to be bound, but just not tightly coupled. And they're still going to have high cohesion because they'll depend on interfaces, and only the interfaces that they need. And now you should follow the principles and make your code rock solid. There's one more thing. I'm an iOS developer, so you can't do a presentation without having the one more thing. Let me reassure you, I'm not about to announce liquid glass. Pun intended. I am, however, going to announce that this talk has 2 parts. Because what's an alternative paradigm that we can use to still get solid code? Anyone? What's an alternative paradigm? No cookie to win, but for the glory, what's an alternative programming paradigm that we could use instead of writing object-oriented, for example? Yep. Exactly. So this talk has 2 parts. Let me reassure you, it's over. People, you can wake up. But I will be doing a talk about functional programming in the near future, so please stay tuned. And now the talk is over, but I'd just like to say a couple of words. I learned how to code in January 2022, so super recently, well, relatively recently. I had not written a single line of code, and never in my wildest dreams would I have thought that I would be standing in front of all of you, giving this talk and having so much fun. It's been an absolute pleasure to be able to talk to you about these principles today. I hope you had at least half of the fun that I had doing and preparing this talk and giving it. So thank you all for being here. And I want to also thank from the bottom of my heart all the organizers. I don't see them here, but we can thank them all. This is an amazing event, and I've already had so much fun. And again, if you're in the audience, in particular if you're a woman, I think it's an incredibly rewarding experience to give a talk. So if this is something that interests you, please apply to the CFP. For the little anecdote, I applied to the CFP about 2 hours before it closed. I was convinced that I was going to get refused, and here I am standing in the Grand Théâtre du Grand Palais de Lille in front of all of you, blabbering on about interfaces and stuff like that. So Yeah, thank you so much for coming to my talk. I know the other talks were also amazing, so thank you for coming to my talk. And now you can ask me anything if there are any questions.